Hello viewer, you are watching R.A.M TV. Welcome to Form 2 Chemistry Lesson 2, and the topic is structure of the atom and the periodic table. I'm your teacher, Benjamin K. Makanda. Stay with me. Now, specific objectives of the lesson. By the end of this lesson, the learner should be able to define atomic number, mass number, isotopes and relative atomic mass. The learner should also be able to calculate the relative atomic masses from isotopic composition. So these are some of the specific objectives that we aim at achieving. And the lesson is going to follow the following order. 1, we are going to review lesson 1. Then definition of atomic number, mass number, isotopes and relative atomic mass. That's another thing that we're going to look at. Then after that, we shall also look at calculation of relative atomic masses from isotopic composition. Thereafter, I'll leave you the homework that you'll attempt in relation number refers to the number of protons in the nucleus of an atom. What's the atomic number of chlorine given that it has 17 protons? 17 is correct. The atomic number of chlorine. Of calcium with 20 protons in the nucleus. You give me your feedback at the end of the lesson. We proceed on. Now, atomic number we said is the number of protons in the nucleus of an atom. Therefore, atomic number equals to number of protons. Atomic number equals number of protons. Now, atoms of each element have different atomic number and consequently vary in size and mass. So, when you take an atom of chlorine and you take an atom of sodium, they are not of the same size, because it's the atomic number that determines their size. For example, an atom of sodium has 11 protons and therefore its atomic number is 11. And an atom of chlorine has 17 protons and therefore its atomic number is 17. When you compare the sizes of these two atoms, chlorine is bigger than sodium. This is determined by the atomic number of that particular atom of a given element. Then, another thing that we have to say about atomic number is that elements are arranged in the periodic table in order of increasing atomic number. So that in the periodic table, we arrange elements starting with element with the low atomic number, moving on to elements with the higher atomic number. Just to give an example, hydrogen has 1 proton and the atomic number of hydrogen is 1. And therefore in the periodic table, the first element that appears is hydrogen with the atomic number of 1. Calcium has 20 protons and therefore its atomic number is 20. So if we have to enlist this element, hydrogen will start as element number 1 on the periodic table, while calcium will be the last one with the atomic number number 20 will be the last on the periodic table. And that's why we are saying elements are arranged in the periodic table in order of increasing atomic number. And we are able to see this from this chart here. Now look at the arrangement of these elements. Element, atomic number, number of protons. Hydrogen 1, atomic number of 1, then number of protons is 1. Helium 2, number of protons is 2. Lithium 3, number of protons is 3. Beryllium is 4, number of protons is 4. And boron 5, number of protons is 5. We can list this one down up the element number 20, which is calcium. 20 atomic number, number of protons is 20. You can complete this table for me. So we proceed on. Having said that, we now want to look at a different term here used in the structure of atom and periodic table, and this is mass number. What is mass number? Mass number refers to the sum of protons and neutrons in the nucleus of an atom. So we are introducing an aspect of the sum, and the items we are identifying in this definition is protons and neutrons. It means that when you take protons and you add to neutrons, the resultant is what we call as mass number. So mass number is the sum of protons and neutrons. Take protons, add to neutrons, then you get the mass number. I give an example. Sodium has 11 protons and 12 neutrons. What's the mass number of sodium? You will take 12, add 11, and the answer you get is that 23. 23 becomes the mass number of sodium. So we also have another example here. Mass number we are saying is the number of protons plus neutrons. And if we go by the example, for example, potassium has 19 protons and 20 neutrons. What is potassium's mass number? It has 19 protons and 20 neutrons. So how do we proceed? Mass number equals to protons plus neutrons. And therefore, 19 protons plus 20 neutrons, what do you get? You get 39. So what is 39? 39 is the mass number of potassium. So you are able now to understand that if you want to calculate the mass number, you add protons to neutrons. So we move on. Now we want to look at a summary of atomic number and mass number, because we have identified three aspects here. We have looked at protons, neutrons, and in our last lesson we also looked at electrons. These three are called subatomic particles. Now we want to relate them to see if they relate in a way. So let's look at this. Atomic mass and mass number. So number of protons equals to number of electrons. Is this true? Yeah, this one is very true, because we said a neutral atom has equal number of electrons and protons, and therefore any uncharged atom is electrically neutral. So number of protons is equal to the number of electrons. That's very right. Then the other one here is mass number is equals to protons plus neutrons. We have just discussed this. Mass number is equals to protons plus neutrons. Let me refer to the example I gave for potassium. 19 protons plus 20 neutrons, you get 39. That one becomes the mass number. 19 stands for the number of protons, 20 stands for the number of neutrons. Therefore, mass number equals protons plus neutrons. The other one here is neutrons. How do you get neutrons? From what we have highlighted there, neutrons is given by mass number minus protons. Neutrons is equal to mass number, subtract protons. Again, let us refer to the example of potassium. We realize that the mass number of potassium is 39. So when you take 39 minus 19, which is the atomic number of potassium, what do you get? Definitely 20. So 20 becomes the number of neutrons in potassium. So neutrons is equal to mass number minus protons. Then, how do we get protons? Protons is equal to mass number minus neutrons. Protons is given by mass number minus neutrons. So mass number of 39 for the case of potassium minus the number of neutrons, which is 20, you get 19, which is the number of protons in potassium. So that one gives us a summary of the relationship between among these three. Now let's look at atomic mass and mass number as a summary of what we have discussed. And we have this table here. Let's look at the table. This table has element, the symbol of the element, the atomic number of the element, mass number, number of protons, number of neutrons, and number of electrons. We begin with the hydrogen. The symbol of hydrogen is H. It has atomic number of 1, mass number of 1, number of protons is 1, number of neutrons is 0, and then number of electrons is 1. One thing you identify here is that number of electrons and atomic number is the same, because the number of protons are equal. The second one is lithium. The symbol is Li, and L is capital, then I is small. Then you have atomic number of 3, mass number of 3, number of protons is 3, number of neutrons is 4. Therefore, how do we get the mass number? We have it as 7. And the other one that we have chosen here is sodium, in that order, then calcium, magnesium. So you can complete the rest using this table. The table can guide you to complete the remaining so that you can add up to 20. Now let's move on and we look at a different thing from this. Now we want to look at nuclide notation. Nuclide notation. Now the word nuclide comes from the word nucleus. So, and in the nucleus, a nucleus of an atom has protons and neutrons. So sometimes when you want to represent whatever is contained in the nucleus, there is a chemical way in which we write this. So nuclide notation refers to the representation of an atom of a given element by indicating the atomic number A as a subscript to the left of the symbol of an element, and the mass number Z as a superscript to the left of the symbol of an element. Therefore, when you get A stands for the mass number, atomic number, and Z stands for the mass number, which is expressed as a superscript to the left of the symbol of that particular element. So when we write an atom of an element with atomic number and mass number represented, then that is what we call nuclide notation. Let's have a view of this. So we have this one here. Yes, our chemical symbol for the element is X, and therefore our mass number is A. And how do you get mass number A? Mass number A is given by Z plus N, where Z is the atomic number, which refers to the number of protons, and N is the number of neutrons. Then down here, we have atomic number, which we write using the letter Z, and Z stands for the number of protons, whereas N is the number of neutrons. So when you write an element, atom of an element, in this manner, then we say, or we call this kind of representation as nuclide notation, showing atomic number and mass number on the left of the symbol of the atom of any given element. That is what we call nuclide notation. Now, having said that, let's now move on to something new, and this is going to be called relative atomic mass. We call it as R.A.M. We call it R.A.M. in short. R.A.M. stands for relative atomic mass. The term there is relative, meaning that you are relating to another component. So what is the relative atomic mass of an atom of a given element? The relative atomic mass of a given element is the average mass of atoms of an element to 1 out of 12 of the mass of an atom of carbon-12. So we specify here carbon-12 because, carbon is an isotope, as we're going to see, and we have carbon-12, we can also have carbon-14. But now, when we compare the mass of any given atom of an element, we have to relate that one to the mass of carbon-12. So that is what we call relative atomic mass. Relate the mass of an atom to the mass of another element that is identical, and in this case we have carbon. So how do we calculate the relative atomic mass? Relative atomic mass is given by mass of one atom of the element divided by 1 out of 12 mass of one atom of carbon-12. Just an example, relative atomic mass of sodium equals to mass of one atom of the element sodium, which is going to be 23, divided by 1 out of 12 of mass of one atom of carbon, which is going to be 1 out of 12 times 12. And you will get the relative atomic mass of sodium to be actually 23, because 1 out of 12 multiplies with the 12, we get 1, so it becomes 23 divided by 12, will remain with 1. Okay, actually 23 divided by 1, you have 23. So the relative atomic mass of sodium becomes 23. So that's what we mean by relative atomic mass. This term, relative atomic mass, is closely related to another term that I'm introducing here called isotopes. Isotopes. What are isotopes? So we define isotopes are atomic number, but different mass number. Atoms of the same element that have the same atomic number but different mass number, we call them isotopes. For example, a good example of an isotope here is chlorine-35 and chlorine-37. They have the same atomic number. The atomic number of chlorine is 17. While their mass numbers are different, we have chlorine-35 and chlorine-37. So these ones are called isotopes. The opposite of isotope is an isobar. You can write it somewhere for your reference. Isotopes, atoms of the same element with the same atomic number but different mass number. The opposite of this one is an isobar, which we'll be discussing later on in our chemistry. Now, let's look at an example of an isotope here. These ones are our isotope. So from the isotope, we have mass number is equal to the protons plus the number of neutrons. So here, we are having this isotope, it has 6. The first one has 6 protons and 6 neutrons. Therefore, the mass number is 12. The second one has 6 protons and 8 neutrons. Therefore, what's going to be the mass number of this one is going to be 14. Whereas the atomic number is the same, 6. Their mass numbers are and 14 respectively. So this one qualifies this atom of this element to be called an isotope. Other examples of isotopes include isotopes of hydrogen, and we have it here. Hydrogen with one mass number of 1, we call it hydrogen 1. The other hydrogen that has the mass number of 2, we call it deuterium. It has 1 proton and 1 neutron. Then the hydrogen with the mass number of 3, we call it tritium with 1 proton and 2 neutrons. This yet another example of isotopes. The other one is an isotope of lithium. We have lithium 6, lithium 7, and lithium 8. That is to mean mass number of 6, 7, and 8 respectively, while the atomic number will remain as 3. Other examples of isotopes that we want to look at here are oxygen isotopes. We have oxygen 16, 17, and 18. Mass number of 16, 17, and 18. While the atomic number of the 3 isotopes of oxygen remains 8. It's only their mass numbers that are changing. So one thing I want us to understand here is that the mass number of a given element is determined by the number of neutrons in the nucleus of an atom. That's why a given atom of an element will have the same atomic number. However, their mass numbers will differ on the basis of the number of neutrons within their nucleus. Now, up to there, let's summarize or look at how we can be able to calculate the relative atomic mass from isotopic composition. Calculation of relative atomic mass from isotopic composition. And then we have it here. So we have isotopes of chlorine. We have chlorine with a relative isotopic mass of 34.696, and the percentage abundance is 75.80. The next isotope of chlorine is chlorine with relative isotopic mass of 36.966, and the relative abundance is 24.20. So how do we calculate the relative atomic mass of these 2 isotopes of chlorine? So this is how we proceed. We first of all identify the formula of calculating the relative atomic mass, and it's given by relative atomic mass. So A subscript R stands for the relative atomic mass. That small r stands for the relative, and A atomic. Relative atomic mass is given by the relative atomic mass of isotope X1. There are 2 isotopes. Isotope X1 times percentage abundance of that isotope plus the relative atomic mass of isotope X2 times the percentage abundance of that isotope, all divided by 100%. So let us substitute from the sample that we have. So we are going to have this. Relative atomic mass of chlorine is going to be given by 34.969 times 75.8, which is isotope X, plus 36.966 times 24.2, which is isotope X2, all divided by 100%. We are dividing with 100 because 100 is the baseline where all other numerical values are compared. So we have this. Now we move on. So when we calculate this, we are going to get 2650 for isotope X1 plus 894.58 for the isotope X2, all divided by 100. And therefore, the relative atomic mass of this element is equals to 2 seconds. Calculate that for me. What do you get? Look at your value. Have you got something like this? The relative atomic mass of chlorine equals to 35.45 atomic mass units. Relative atomic mass of atoms of elements are measured in atomic mass unit. So this one becomes the relative atomic mass of chlorine atom, which is approximately equivalent to 35.5 atomic mass units. Now, up to there, I now want to leave you with one task that you will complete at the end of this lesson that we will discuss when we meet next in our next lesson. So this is what you're going to do for me. Work out the number of protons, electrons, and neutrons for these atoms. Work out the number of protons, electrons, and neutrons for these atoms. So these include helium-4, 2, number 2, nitrogen 14, then fluorine 17, sodium 23, and potassium 39. This is the work that we'll do so that when we meet next, we'll look at it before we proceed. Up to there, I've been your teacher, Benjamin Makanta. Until next time, stay tuned.